Greetings, my young math Padawans. This is Chapter 7. That's right, Chapter 7, Rational Functions. And in this section, we're going to talk about graphing rational functions. Now, I'm going to kind of go through some of this kind of quickly because between the Desmos activity that you did last class and this lesson, you should have a full picture of what it means to graph a rational function. But first, let's start with the basics. What is a rational function? A rational function is essentially when you put one equation over top of another equation. Now, more specifically, a polynomial over another polynomial. We sometimes use this form right here, P of x over Q of x, just kind of as a way to denote a rational function. There is a more complicated way, but I'll show you that later on, not today. The most basic rational function looks like this, f of x equals 1 over x. And that is essentially just the plain old parent function, no transformations done to that. If we were to look at this graph, it would kind of give us an idea of the shape of what rational functions look like, provided they're in a certain form. So let's start by doing this. Why don't you pause the video right now and let's see if you can create that good old table of values that we always use. That table of values for the function 1 over x. So go ahead, pause the video right now and see if you can do that. I bet your table of values looks a little something like this, right? Where you have your x values and you probably went from -3 to +3 and you have some bunch of decimals. Hold on a second, what's going on here? And even more so, when you try to plot the points, they look a little something like this. It's really hard to see exactly what this graph looks like. And that's because of kind of the nature of the numbers that we're working with and the way this function works. So here's what I'm going to do. I'm going to look at some more values that are right here between -1 and 0, like some fractions in there. And I'm going to look at some more values between 0 and +1. And I'm going to kind of expand my table of values a little bit more. Make it look like this. Now, I'll do the math for you, but remember, like if you're going to plug in like 1/2 into this equation, right? If you're going to make x equals 1/2, when you do the math for that, you need to remember to do 1 divided by 1/2. Or if you're going to put that in the calculator, it would be 1 divided by, and then a parentheses, that 1/2. You got to make sure you use parentheses in this problem. Or if you're using one of my calculators, it would look a little something like that. But make sure your fractions in parentheses if you're working along, or this isn't going to work out the way you think it should. When I expand that table of values, I get some more numbers. You'll see when I plug in -1/2, I end up with -2. -1/3 turns into -3. 1/4 turns into +4. Go ahead, try in your calculator. Pause the video real quick. This should take you like 10 seconds. And just make sure that you can get these values by using your calculator. Okay, now I'm going to take this table of values, this expanded table of values, and I'm going to plot points. Notice on the next graph on the next screen, you'll see my blue points were these integer values that I plotted, and the green points will be these fractional ones that I've added to the table. So take a look. This is what the graph looks like. Now, you'll notice that I'm kind of traveling along these two curves. It's two separate curves, but I want you to understand that this is one graph. And there's a couple important characteristics I want to point out with this graph. You'll see this imaginary line, this x equals 0 line, and we call that a horizontal asymptote. That's this word right here, asymptote. Horizontal asymptote. And simply what that means is as my x values get bigger, my y values are going to get closer and closer to 0. If you go back and look at that table of values, or right now in your calculator, if you start putting in like 1 over 10, 1 over 100, 1 over 1,000, you'll notice that those numbers are going to get closer and closer and closer to 0. That happens in both directions. As my x values get bigger, or my x values get smaller, my y values get closer and closer to 0. We would say that with this notation, f of x goes towards 0 as x goes towards infinity. I just noticed a little mistake up there. Anyways, the other thing that you will notice is that as my x values get closer and closer to 0, my y values get bigger and bigger and bigger. My y values go towards positive infinity. Or if I'm looking at it on the left-hand side, as my x values get closer and closer to 0 here, my y values go towards negative infinity. or it gets smaller and smaller and smaller. That's a really interesting characteristic that this graph has. We call this imaginary line a vertical asymptote. So essentially what an asymptote is the long-term behavior of a function. Not what's happening in here, but what happens on the ends of my function. What happens on the ends of my function. The other important thing to a characteristic of this function is the domain and the range. And these asymptotes, our line cannot cross the asymptotes or will not cross the asymptotes in this particular function. So pay attention and notice that the domain is x cannot equal 0. So that's this value right here. My x value is not going to equal 0. I have this imaginary line that my line never crosses. And my range is y cannot equal 0. That's this horizontal line that I have. Y cannot equal 0. As we look at different versions of these functions, the domain and range will change. And we actually had some transformations, and you should have saw that from the lesson and from that Desmos activity that you did earlier. So here is the parent function with some transformations performed to it. So one of the things that I want you to know and want you to be able to figure out here is this line right here, this vertical line that goes up and down, x equals h. That's going to be whatever the h value is. And then this line right here that's going horizontally, that's always going to be y equals k. So whatever the k value is, that's going to be the line. And again, if you think about this in terms of transformations, we would shift our graph to the right or left h units and up or down k units. And then A just talks about how close does my curve actually get to the line. Is it like way out here? Or is it really close and tight into the graph? So that's kind of what A will affect. A will also, just like with our other graphs, do a reflection if it is. So let's take a look at an example of this. So we're going to graph -2 over x minus 1 plus 3, and then we're going to state the domain and the range. Okay, first things first. I want you to understand that this graph moved to the right 1 unit, right? That's from this right here, and up 3 units. That's from this right here. Okay, we also had a reflection. And we'll get to the 2 and what the 2 actually does in this particular problem here in a second. Okay, but remember what my parent function would have an asymptote here and here on my 2 axes, right? My x-axis and my y-axis, okay, would have my 2 reflections. But I moved it to the right 1 unit. So since I moved it to the right 1 unit, I now am going to have a vertical asymptote here at x equals 1. Okay, and I'm going to have a horizontal asymptote because I moved my graph up 3 units. I'm going to have a horizontal asymptote here at y equals 3. Okay, and that's the same thing as what I told you before was going to happen on the last slide. So let's just label those separately. Let's say we have asymptotes. Okay, and we have this. We have a vertical one at x equals 1. And a horizontal at y equals 3. Okay, those are my 2 asymptotes. Okay, now my graph. So normally my graph would go up here and down here, but since there was a reflection, right, I'm going to have to graph it in the different quadrants. And I think, you know what, it might not be a bad idea if you're a little confused about this to create for yourself a table of values. And I'm going to use some basic numbers. Like I'm going to look and say, ooh, how about 0 and -1? That might be 2 values to figure out where they are. And not at 1 because there's an asymptote there, but probably like 2 and 3. So here we go. So I'll go at -1 and 0, and I'll plug in some values, and then maybe like 2 and 3, like I said, because 1, there's an asymptote. It's pointless to plug that in the calculator. So I'll plug -1 into my equation. Okay, so -2 over -1 minus 1 plus 3. And let's see here, that'll give me -2 over -2 plus 3, which is 1 plus 3, which gives me 4. I'm going to be real careful when I plug these numbers in my calculator, but I'm going to do the same thing for these other values. And then I'll plot the points. So -1, 4 puts a point here. 0, 5 puts a point here. 2, 1 puts a point here. and 3, 2 puts a point here. Now that should be enough for me to to sketch the graph here. Okay, and I'm not worried about it being very exact here, but just close enough. You'll see that I'm making my line run towards the asymptotes and not crossing them. And that's what the graph of -2 over x minus 1 plus 3 looks like. Now, let's go ahead and talk about the domain and the range, okay? The domain is any x value that my function's defined for. Well, I got all these x values that work. I got all these x values that work. The one that doesn't work is at 1. So my domain is x cannot equal 1. What about the range? The range. Well, it's the same idea here. I got all these y values that work, right? Those y values work. These y values work. The only y value that doesn't appear to work here is at 3. So y can't equal 3, my domain and my range for this function. Do you remember what I told you about the domain and the range being all real numbers unless you convince yourself otherwise? This is one of those instances where you need to convince yourself otherwise because we can't divide by 0. So if you think about this 1 right here, 1 being plugged in here would give me -2 divided by 0. And that's no good. Mathematically, we can't get over that. So we simply say x can't equal 1, and all of the other numbers work. Okay, so here's the point where you're going to pause the video right now, and you're going to try to graph these 3 functions. Please use the idea of asymptotes. Identify the asymptotes, state the domain and the range, sketch a picture of the graph. You can do this using the idea of transformations. And I will show you those graphs here momentarily. So pause the video right now and try to sketch these graphs on your own. Good luck. Okay, here's the first one, 3 over x minus 2. So this hasn't been shifted to the right or the left at all, but I have gone down 2 units. There's also not a reflection. Okay, so when I'm graphing this, I know I'm just going to have a horizontal asymptote at at -2, and a vertical asymptote at 0 because there was no shift that happened. So now I'll just go ahead and do my table of values. I'll do my table of values real quick. It's going to look like this. I can plot these points, and I can connect the dots, making sure that I kind of make my curve travel towards the asymptotes. That's what this graph looks like. H of x is equal to -1 over x plus 4. Okay, you should have saw that this moved to the left 4 units and was reflected. So what does that mean? Since I just moved to the left, that means that my horizontal asymptote is still here at 0. But I did move to the left 4 units, which means that I now have a vertical asymptote here at -4. I'll create a table of values for myself that'll look like this. And I'll plot those points here. I went a little off my graph, but that's okay. And get the idea of what's happening here. Looks a little something like this. Now, I forgot to do it in my last problem, but I'll do it here. I forgot to state the domain and the range. In this problem, the domain, x cannot equal -4, and my range, y cannot equal 0. P of x equals 1 over x minus 1 plus 5. You should see that this moved to the right 1 unit and up 5 units. I'm going to be in trouble with this graph, but it's okay. Right 1 unit puts my vertical asymptote here at x equals 1, and up 5 units puts my horizontal asymptote here at +5. So again, that vertical asymptote at x equals 1 and the horizontal asymptote at y equals 5. I'll create a table of values and plot those points. And that will give me the graph. And again, I'm off the graph here a little bit, so hopefully you adjust it on yours. We'll make it go towards these asymptotes and look a little something like this. Okay, again, domain. Domain, x can't equal 1. Range, y can't equal 5. All right. Now remember, rational equations are in the form of any polynomial over any other polynomial. And the more complicated the polynomial, the more complicated the rational equation looks like. So we'll start with an easy one here, and then we'll get into some more general rules. But for a rational equation that has a linear equation over another linear equation, we can come up with 2 kind of basic formulas for the horizontal and vertical asymptotes. So the horizontal asymptote, again, ax plus b over cx plus d. The horizontal asymptote is a over c, y equals a over c, and the vertical asymptote will be negative d over c. Let me tell you where these come from. The horizontal asymptote is kind of what's happening as the x values become bigger and bigger and bigger. The x values are going to get bigger. So essentially what happens is these numbers stop mattering so much, and it ends up just being a over c. A over c. It just ends up being those values right there as my as my x values get bigger and bigger. Those are the only numbers that are actually going to matter in the long run. That's a horizontal asymptote. The vertical asymptote is a little bit easier to talk about because that's when the denominator equals 0. So in this case, cx plus d equals 0. And we're simply going to do some algebra, and we're going to solve for x. So if you ever forget, you can always just set the denominator equal to 0, and that's how you're going to end up with your vertical asymptotes. Every single time this works. Let's see how we graph these. So here we have f of x equals 3x minus 1 over x plus 2. We're going to graph that, then we're going to take a look at the domain and the range. So the good news is this equation looks exactly like our other ones did, but that's only when they're in the form of a linear equation over another linear equation. So the first thing we're going to do is we're going to figure out where the asymptotes actually are here. So the asymptotes. And according to what our previous slide, our horizontal asymptote happens at y equals a over c. And in this particular problem, my a value is 3, and my c value is this number that's right here in front of that other x. So that's 1 here in this particular problem. So that's at y equals 3. I'll go ahead and draw that in on my graph over here. Y equals 3 would be that guy right there. Okay, what about the vertical asymptote? Vertical asymptote is at x equals, now again, it's the opposite d over c, the opposite of d over c, but I never remember that. I'm just going to forget it every single time. So what I do is instead, I'll set the bottom equal to 0. So in this case, x plus 2 equals 0, and I'll end up with x equals negative 2. Now, if you did do that opposite of d over c business, right, the d value is 2. So you get the opposite of 2 over, and again, that same c value, 1. You'll see I end up with the same exact thing, but I think setting the bottom equal to 0 is a much better and safer route. And I got to be honest with you folks, spoiler alert, it's going to help us in future problems. All right, so I'll go ahead and graph that x equals negative 2 now. That's the line right there, x equals negative 2. And now, just like I did in the other problems, I think a couple points might be helpful for me. So I'm going to look at the value of the function at, I don't know, I want to do maybe 2 points over here. So I'm thinking like negative 3 and negative 4. So negative 3 and negative 4. And I'm thinking like 2 points over here. So how about negative 1 and 0? Negative 1 and 0. And I'll plug those into my equation. So I'll take that negative 3 and I'll put it into my equation. Let's see here. So that'll be 3 times negative 3 minus 1 over negative 3 plus 2. When I do that, I get, well, let's see here. That's negative 9 minus 1. So that's negative 10 over negative 1. So I get positive 10. And when I plug in negative 4, I'll just do the math for you. I get 6.5. So we'll go ahead and plot those points. So that's here. Negative 3, 10 is like all the way up here. And negative 4 is 6.5. Negative 4, that's 5. So probably about like there. And again, and then if I plug in negative 1, I'm going to end up with negative 4. And if I plug in 0, I get negative 1/2. So I'll plot those points now. Negative 1, negative 4, that's all the way down here. And 0, negative 1/2 is here. So I can get a really good idea of what the graph would look like. So I'll just go ahead and draw it in a little something like this, okay, towards the asymptotes. Really spread out in this particular graph. The great thing is you can check these all in Desmos if you wanted to. Just plug it in Desmos, see if your graph that you sketched matches what you came up with when you did it on paper. Last thing there is to do is state the domain. Domain, let's see here, it's not at that asymptote. So x does not equal negative 2. And the range, y does not equal that vertical or that horizontal asymptote 3. these aren't that bad, especially when you find those horizontal and vertical asymptotes first. So you may be wondering what the connection is between this linear form that we're working with now and that original transformation form that we worked with in the beginning. Well, we can convert from one to the other, and it's actually pretty easy. All you have to do is use long division. That's right. With some long division, we can actually figure out how to write from one to the other. So we're going to convert 2x plus 5 over x plus 2 to that vertex form. So what we're going to do is we're going to do the division. So we'll take that x plus 2 and divide it into 2x plus 5. Now you got to remember how to do all this division. So remember, what times x will give me 2x? I'm not going to spend a lot of time on this because this is the second time you're seeing it. So I am expecting that you remember how to do this long division and come up with the answer with the remainder of 1 down here. So we see the remainder of 1. So remember what this means. This means that the result is 2 plus 1 over x plus 2, right? We put the remainder, this remainder up here on top of the fraction. Now I do just want to adjust the form just a little bit, so I'm just going to rearrange it and write it 1 over x plus 2, just to make it match up with that form of the equation that we came up with. So by doing a little bit of long division, we can see the relationship between this linear over a linear equation and that original transformation form of the parent function. So let's take a minute right now, and I'd like you to try these 3 problems, number 4, 5, and 6, where you're going to graph the first 2, and then we'll do one where you convert to that transformation form. So go ahead, pause the video right now, try these 3 problems. We'll go over them momentarily. Go ahead, pause the video. No, really, pause the video and try it. Okay. Okay, so first things first, we're going to figure out where the asymptotes are. So, where are the asymptotes? Okay, first we'll do the horizontal asymptote. And remember, that's going to be y equals that a over c. So in this case, 1. And then the vertical asymptote, where's that going to be? Remember what I do. I set that denominator equal to 0 and I solve. So I get x equals negative 3. I'll go ahead and draw those on my graph. Here's y equals 1, and x equals negative 3 is right here. I'll come up with my table of values, my x and my f of x. And let's see here, I'll pick, I don't know, negative 5, negative 4, and then how about negative 2 and negative 1? I'll plug those into my equation, and I'll end up with these values. I'll plot the point. Negative 5, 3, negative 4, 5, negative 2, 3. I'm sorry, negative 3 I meant, and negative 1, negative 1. And I'll graph it in there. Looks a little something like this. Domain, x can't equal negative 3. Range, y can't equal 1. All right, next one. Again, we'll find the asymptotes. And the horizontal asymptote is a over c, or negative 3 over negative 1, which simplifies down just to 3. And the vertical asymptote, I'll set the denominator equal to 0, and I will solve that and end up with x equals negative 1. So I'll graph those. Y equals 3, x equals negative 1. I'll come up with a table of values. Just like so, I'll plot the point. Negative 3, 4, negative 2, 5, 0, 1, and 1, 2. Knowing what I know about these graphs, I can then sketch a really good picture of what this looks like. Domain, x can't equal negative 1. Range, y can't equal 3. One more problem to go. We're going to convert 2x plus 3 over x plus 1 to that transformation form. And we're going to do that by doing the long division. Okay, so what times x will give me 2x? Of course, there would be a 2. That'll give me 2x plus 2. I'll make sure I'm subtracting so that those go away, and I'll end up with 1 as being the remainder. So my answer, 2 plus 1 over x plus 1. But to get it into that vertex form, h of x equals 1 over x plus 1 plus 2. Just do a little switcheroony. Final answer. All right, folks, hope this made sense to you. Be sure to ask me any questions that you may have when we go over this in class. See you then. Good luck, folks.